All right, theoretical probability. We're going to move away from the experimental, from actually doing things, collecting data, to what do we expect to be happening? How many ways can something happen out of the total possible ways that anything can happen? So 3 coins are tossed, write down a list of all possible outcomes, then find the probability of these things. So 3 coins are tossed. Head, head, head. Head, tail, head. Head, head, tail. Tail, head, head. And then we've got tail, tail, head. Tail, head, tail. Head, tail, tail. Or we could have tail, tail, tail. And I think I have them all. And it can be difficult when there's a bunch of things happening to do this. And this is where it becomes nice to have a tree diagram. We could get heads or tails on the first event. Then after that we could have heads and tails, heads and tails. Then we continue this on, heads, tails, heads, heads and tails. And then once we're done here, it's just a matter of following each branch to write down all of these possibilities. So now we need probability. Find the probability of getting 3 heads. Well, that happens exactly one way out of the total 8. B, at least 1 head. At least 1 means 1 or more. So how many of these have 1 or more heads flipped? 7 out of the 8. 3 heads if it is known that there is at least 1 head. Okay, this one gets a little more complicated. So now we know that there has to be at least 1 head. That means we know that that's not a possibility anymore. So now there's only 7 total possible outcomes. And out of those 7, how many have exactly 3? 1. 1 out of 7. Knowing that there's at least 1 head reduces the possible sample space. Second example, so we have a special die. On this die there is 2 zeros, 2 ones, a 4, and a 5. It's rolled twice. And it says illustrate the sample space with a 2-dimensional grid. All right, 2-dimensional grid. X and Y axis. We're going to write all the possibilities for the first roll. And for the second roll. There we have it. And it looks like we're adding the numbers up for part A. So a total of 5. So if I'm going to write down totals here and think about these totals, well, first let's figure out how many items are in this sample space. So can you sort of see what this ends up being? It's looking like a rectangular grid that is 6 by 6. A rectangle that's 6 by 6 has an area of 36. So 36 total outcomes. And I want a total of 5. So 0 plus 0, that's not 5. We need to go through here and find where we have a total of 5. So 5 plus 0, this one. That one. Those two up on the top, 5 plus 0. Then 1 plus 4 also works. So 1 plus 4, that's those two and those two. Are there any other ways that we can roll a sum of 5? And the right answer you should be thinking to yourself is, no way, man. There's no other way we can get that. So this probability for part A is equal to 1, 2, 3, 4, 5, 6, 7, 8 out of 36. And 8 out of 36 reduces to 2/9. Part B, two numbers which are the same. Those four that I just highlighted, those four outcomes, all represent where I roll a 0 on both rolls. Those all represent where I roll a 1 on both rolls. There's a 4 on both rolls and a 5 on both rolls. So this probability for part B is 10 out of 36, which is 5 over 18. And both of these are instances where I would consider these fractions to be nice. They're relatively small. I would leave these as fractions and not change them to decimals. It's just less work for me, the mathematician, doing these calculations.